I sat down to grade these quizzes that you guys were working on last week, and right away I saw some things, so I want to get these straightened out so that we don't continue to make these same mistakes. First, be careful when you're doing these problems. This one, you guys all drew this sled going uphill. It doesn't say the sled's being pulled uphill. It says it's being pulled along the ground at a constant speed by a force of 30 newtons acting at 50 degrees above horizontal. Okay, so when you pull like a wagon or a sled or something, you don't pull it, you don't go down on your hands and knees and crawl around with it, you pull a little bit up on it, right? So the sled is here, and you're pulling up this way, okay? This is 50 degrees, this is 30 newtons, this is of course the force due to gravity, this is the normal force, and this is friction, okay? Force due to friction. Now, all those forces are acting, and it said to label them all. Okay. Now you guys drew this going up an incline, which, I mean, if you had a 50-degree incline, that would be impossibly steep. But then your 30 Newton force would be this way. But you still would have gravity, and you still would have a normal force, and you still would have a frictional force. And you guys didn't draw those. Okay. All those forces are on that sled, so make sure you're paying attention to all those forces. This, by the way, this is not how it's set up, so I don't want to do that one. But I am going to mention it one more time as we come down here. It says determine the work done by the applied force on the sled. Well, the applied force is this 30 Newton force. Okay. Now, the equation for work is work equals force times the change in position times the cosine of the angle between them. As long as we're looking at this, then the displacement is to the right and the force is up, and so this would be 30 times the distance, 20, times the cosine of 50. Okay, and when you work that out, you get about 386 joules or so. Okay, now that's if you drew the picture right. You guys all drew the picture like this. Okay? If you draw your picture like that, then the force is up the incline and the motion's along the incline. Then you would say the work done is 30 times 20 times the cosine of 0. And the cosine of 0 is 1. So this would just be 600 joules. Okay? So you only have to deal with the cosine of the angle if there's an angle between the force and the motion. If there's no angle between the force and the motion, then you don't have to worry about it. The work done by friction on the sled. Alright, now, this is easier now that we know the work energy theorem, but we didn't know the work energy theorem when I assigned this. Okay, so it says the sled is moving at a constant speed. So if you think about that, okay, that tells you that this 30 newtons this way and the frictional force this way have to sum to 0, because the net force is 0 if they're moving at a constant speed because the acceleration is 0. Okay, so this 30 cosine 50 is equal and opposite to the frictional force. Okay, now since we're basically doing the exact same thing we did before, okay, the work done by friction and the work done by the applied force are going to be equal, but in opposite directions. This is negative 386 joules. Okay, that's it. Okay? Now, if that's the case, it says D determine the coefficient of friction, then you can find the frictional force, 386 divided by 20, right? Because work is force times distance. Okay, so the frictional force has got to be negative 386 divided by 20, which is 19, almost 19 and a third or so newtons. And so then the coefficient of friction, well, that's just equal to the normal force times the coefficient of friction. Of course, then you have to find the normal force, and the normal force is not equal to mg. Okay, the normal force is mg minus the vertical component over here. Okay, so you'd have Fn equals mg minus 30 sine 50. And then you can sub that back in and solve for the coefficient of friction. It's fairly small. It's a sled, so it's being pulled across snow. All right. Number 2, a little bit better on number 2, but you guys are still making a couple mistakes here. Okay, you push a 4 kilogram cart with a force of 12 newtons over a distance of 2.5 meters. So here's my cart, 4 kilograms, 12 newtons, distance of 2.5 meters. The work you did on the cart, you guys all did this right. Work equals force times distance times the cosine of the angle between them. There is no angle, don't have to worry about it. So 12 times 2.5 equals 30 joules. Okay? It says the size of the frictional force acting on the cart. Well, this is a little bit trickier. It says you moved it 2.5 meters and you caused it to accelerate from rest to 2 meters per second. Net force equals mass times acceleration. Okay, so this 12 Newton force that you guys applied has to be counteracted a little bit by friction, and we got to figure out what that is. Okay, and so we need the acceleration of the cart. So v squared equals v naught squared plus twice the acceleration times the change in position. So it says 2, which is 2 squared, equals 0 plus 2 times whatever the acceleration is times 2.5. Okay, so 4 equals 5a, and a equals 0.8 meters per second. Okay? So then I come over here into my net force equation and I say the net force is the 12 newtons I apply minus whatever friction applies has to equal mass 4 times 0.8. Okay, so 4 times 0.8 is 3.2, and 12 minus 3.2 is 8.8 newtons. Okay, so friction is exerting a force of 8.8 newtons. It exerts that force against the motion over this distance of 2.5. So 8.8 times negative 2.5 is 22, negative 22 joules. Okay? Right. Now there's another way you guys can do this now that we know the work energy theorem. You could say, well, let's just look at its change in kinetic energy. Okay? And it went from rest to 2 meters per second. So delta KE is 1/2 mv squared minus mv naught squared, but that's just 0. So 2 squared is 4 times the mass is 16 divided by 2 is 8. Okay, its change in kinetic energy is 8 joules. Well, if you look at that, you did 30 joules of work, friction did negative 22 joules of work, so yes, it changed by 8 joules. Okay? Alright. Number 3. Don't know why that one's up here. A 900 kilogram car moving at 20 meters per second applies the brakes and comes to a stop. Will the work done be positive or negative? And negative you guys have because force is opposing motion. Excellent. And that gets back to the whole cosine of the angle thing. The angle is 180 degrees, so the work is negative. If the brakes can exert 1200 newtons of force, how far does the car move before stopping? Looks like you guys did okay on that. You found the acceleration, much like we did up above, and then used that to get force and distance, and so everything worked out. Okay, and then how much work is done stopping the car? Force times distance, about 180,000 joules, and then you repeat the whole process down here, and it turns out it's the same. Okay, now why is it the same? Well, now we know it's the same because the work done is the same because the change in kinetic energy is the same. Right? It goes from moving at 20 meters per second to not moving. Even though this force is smaller, still just as much work is done because it has to act over a much greater distance. This force is bigger, stops the car in a shorter distance, but still does the same amount of work. Alright, so be careful in drawing pictures and make sure you're getting all your forces labeled and you're paying attention to direction.